All right, continuing with multiple choice cumulative review, number 19. Let f be a differentiable function. Again, smooth curve, no sharp turns. Differentiable also assumes continuity. Order pair 0, -4, order pair 10, 11 sits on the graph. Which of the following must be true? All these are referring to some sort of a theorem, extreme value theorem, mean value theorem, and IVT. So let's consider what we know about this graph. A graph is differentiable, meaning it's a smooth curve. Then it must also be continuous. That means no breaks in the graph. All right. And both these statements are the conditions needed for mean value theorem, to fulfill mean value theorem. So let's think about what mean value theorem tells us is that function is continuous on the closed interval from 0 to 10, differentiable on the open interval from 0 to 10. Those are both true. And what mean value theorem tells us is if we're given two order pairs and it's a differentiable function, then the slope between these 2 points, whatever that slope is connecting these 2 points, then there's a place on the curve with that exact steepness. So the slope here is 11 minus -4 over 10 minus 0, and that's f prime is equal to whatever that slope is, so 15 over 10 or 3 over 2. But it doesn't go that far. It only makes it to this point, which matches our answer choice. Let's explore the other choices and why those are not correct. F prime of c equal to 0, since extreme value theorem applies. Extreme value theorem is trying to guarantee the highest and lowest points on the graph. But we can't guarantee that there's a slope of 0 on if we're trying to prove extreme value theorem, because extreme value theorem does not require differentiability. So extreme value theorem only requires continuity, and then we're testing endpoints and critical points. The second one, close, but it doesn't quite match what we need for slope. It's not. We're adding the two y values together, but it's changing y over changing x. We should be subtracting instead of adding here. And then intermediate value theorem tells us that if the graph crosses through 0, -4, and 10, 11, then between 0 and 10, it must hit all the y values between -4 and 11. That's what IVT tells us. It's not going to give us any information about slope or derivative, so we know this answer choice is also out. Okay, number 20. We have a function defined by f of x, z over z minus 4 times z plus 2, on which of the following intervals on which can mean value theorem be applied to. So mean value theorem has to be, well, first off, this is going to be a smooth curve everywhere except it's a rational function. So a rational function is going to be smooth as long as it exists. The only thing that could break this apart is places where there are vertical asymptotes or holes. No holes because there's no factor in the numerator that cancels out, but we do see factors in the numerator, in the denominator. So that tells us that we have points where the graph is undefined. So the graph is undefined at 4 and -2. So basically, as long as we're able to see statements that doesn't conflict with these places where the graph is undefined, then we can state that mean value theorem will apply. So continuous between difference between -1 and 3. -1 and 3 is fine because -1 and 3 is going to fall safely between -2 and 4. So between -1 and 3, we're not going to have any vertical asymptotes that's going to break, that's going to cause issues there. Between 5 and 7, we're also safe because our vertical asymptotes are -2 and 4, and between 5 and 7, we're not going to have any conflicts there. The conflict is going to occur between 1 and 5. Between 1 and 5, there is a vertical asymptote at 4, and 4 is going to disrupt that that interval. So therefore, we can't state the function is continuous and differentiable on that interval. So option 3 is out, just 1 and 2. We look for 1 and 2, and that's answer choice C. Okay, 21. Selected values of continuous function f. So it's continuous, meaning there are no breaks in the graph, there are no vertical asymptotes, there are no holes. But this is the only characteristic that we see. We don't see anything about differentiability, so we can't guarantee it's a smooth curve. So keep that in mind, that it says continuous, but it doesn't have to be, doesn't mean that it's guaranteed to be differentiable or a smooth curve. Okay, so let's look at our options here. Which of the following could be false? Okay, so by intermediate value theorem, there's a value such that f of c equals 10. Well, if we want to figure intermediate value theorem, we don't need differentiability. We just need continuity, and we're just trying to guarantee a point that the graph will cross through a y value of 10. We know this is going to be true because you start off with a y value of 1 and you end up with a y value of 31, and it's connected everywhere between. So if it's trying to get from 1 to 31, it's going to eventually have to cross that y value of 10. So this is going to be safe. By mean value theorem, there's a value such that f prime of c is equal to 10. If we want to do mean value theorem, if we're trying to guarantee a slope, we can't guarantee a slope if we're not told that the graph is smooth all the way through. So mean value theorem does require differentiability, and differentiability is not a statement that is provided for us in the beginning. So that condition is not met for sure. So this could fail. Okay, so that's our answer there. But let's look at C and D. By extreme value theorem, we know that every point on the graph is going to be less than or equal to f of x. Extreme value theorem only requires continuity. So if we're trying to find an absolute max or absolute min, as long as the graph is continuous, EVT will apply. Okay, 22. The figure shows graph FF, which of the following could be the graph of f prime, the derivative. So this is the original graph. Okay, so this is what the original graph looks like. I'm just going to create a slope and concavity sign line, and then from there I'm going to build my f prime graph. And once I build my f prime graph, then I'll look at my answer choices to see which one looks closest to the one that I have. So I just created a bunch of points of interest here. So first thing I saw was I'm going to identify the peaks and valleys. Those are ones I want to identify as my sloping 0. So positive slope, negative slope, positive slope, negative slope. I made those points C, D, and E just to kind of give myself some access points on this graph. So C is my relative max, D is the relative min, E is the relative max. And then I just had arrows indicating the path of my graph. Now, I don't know exactly where my points of inflections are, but I'm just going to give a guess, kind of a general guess here. So this resembles concave up, right? It has that concave up shape. And here it becomes concave down, then it becomes concave up, then it becomes concave down. And this is very slight here, but hopefully you guys can see that this goes to concave up. So between all these transitions, between concave up and concave down, there must be points of inflections. So I'm just going to indicate where I best think those points of inflections are. So in red, I use some more letters to indicate those points of inflection, and I created a second derivative sign line, and I identified concavity in each of those intervals. So concave up, followed by concave down, followed by concave up, concave down, and then concave up. So if I want to create an f prime graph, I create, here's my x and y axis. My y axis now represents slope, so I'm going to kind of identify and mark down the parts that I'm looking at with f prime. So anything above the x-axis must be positive slope, anything below the x-axis must be negative slope, anything on the x-axis are places where slope is 0. So slope is 0, x, which are the x-intercepts, will be C, D, and E. So I'm going to highlight, I'm going to mark off those points, C, D, and E. And my graph is going to be concave, it's going to be increasing between A and C. So I know that the graph is going to be above the x-axis, then it's going to end up below the x-axis, goes back to above the x-axis, and then back down to below the x-axis. Now, points of inflections are going to be the peaks and valleys, the relative max and relative mins of my f prime. So here I'm going to indicate a place where there's a relative max, and then there's a relative min there. I call it G, relative max for H, relative min for I. So my graph is going to look something like this. And the concave up, concave down will match with the slope behavior of my f prime graph. Concave up is positive slope. Concave down means negative slope. Concave up, positive slope. Negative slope, positive slope. So here's my f prime graph without looking at the answer choices, and now I can go to my answer choice and see which one matches the best. It's not perfect, but this is going to, answer choice B is the one that displays all the behavior of my x-intercepts and my points of inflection, better than the other choices A, C, and D. Okay, D is close, but it doesn't have as many x-intercepts as I need. Those are missing in answer choice D, so answer choice B is our answer. Okay, 23. A curve in the xy plane is defined by the function. Which of the following statements are true? At -2, there's a place where a horizontal tangent occurs. At -8, there's a place where a vertical tangent occurs. And at -1, 1, there's a slope of 1/2. So we know that all these statements is referring to something that I can find through the derivative. So I first have to find the derivative, and then I can work towards figuring out some of this information. So if I want to find the derivative, notice we have y's mixed into the equation here. I have to go through implicit differentiation. So what that means is, as I go through each of the derivatives, when I come across y, each of the y's derivative will produce a dy dx. So let's go down our terms here. X cubed becomes 3x squared. Y squared becomes 2y dy dx. Right? Y's variable will produce dy dx. 12x becomes 12. 16y becomes 16 dy dx. 28 goes to 0. Now I just want to try to get dy dx by itself. So I'm going to leave the two dy dx terms on the left, move the non-dy dx terms on the right, factor dy dx out, divide over, and I'm going to clean up as much as I can within my derivative function. So I factor the 3 out, factor the 2 out, and I continue to factor through. Now, tangent to the graph being horizontal. So anytime looking for a horizontal tangent line, that is going to be located in the numerator of my derivative. Okay, so numerator of the derivative is where we find those critical points that will lead us to horizontal tangents. The denominator of the derivative function of the derivative equation will give us information about where vertical tangents might occur. So these are important things to know as we prepare for our AP exam. So let's set the numerator equal to 0. I can factor 4 minus x squared to be 2 minus x, 2 plus x. I find horizontal tangents being 2 and -2, and -2 is one of the answer choices that matches my statement, so I know that this is a true statement. Denominator is where I can pull information about vertical tangents, so I set the denominator equal to 0, I get y equals -8, and that matches with statement 2, so that's true as well. And then the third statement, the line tangent to the curve at -1, 1 has slope 1/2. So if I plug -1, 1 into my derivative equation, I should get a slope of 1/2. So I take my derivative equation, plug -1 in for x and 1 in for y. I have that here. And that gives me 12 minus 3, which is 9. 2 plus 16 is 18. 9 over 18 is 1/2. That is also a true statement. So all three statements are true. Answer choice D. All right, 24. We have the derivative of function a given, which is a prime, A of 1.2 is 7.5. If the linear approximation of A of t at 1.2 is equal to 1.2, use it to estimate A of t. At what value of t is there a linear approximation that estimates that A of t equals 15? So we want to gather information to create our tangent line equation first. So anytime we're dealing with linear approximation, let's just worry about creating that line first. Let's gather a slope, let's gather order pair so we can build our linear equation. So our point in our order pair, our point in our slope here, our point is 1.2, 7.5. The slope, we have the derivative here, so we just plug 1.2 into the derivative, and in return we'll get the slope. We have our order pair, we have our slope, so we're going to build our tangent line equation, clean it up, solve for y. So this is where I am after I get y by itself. Now we want to use this linear equation it says if the linear approximation at t equals 1.2 is used to estimate A of t, at what value of t does the linear approximation estimate that A of t equals 15? So we basically want to use this linear approximation to figure out at what t value is y going to be 15. So we can just put 15 in for the y, and then just algebraically try to solve for t. So we can subtract 7.5, divide the 15.066 over, add the 1.2, and that will leave us with t by itself. So t equals 1.6978. 25. Particle moves along the x-axis so that at time t is greater than or equal to 0, the position is given by z of t. What is the total distance traveled by the particle over time? So distance is simply the definite integral from one endpoint to the other endpoint of the absolute value of v of t. So this is our position function. So to get to our velocity function, we can just find the derivative. So to find the derivative, we go through power rule. 2t cubed becomes 6t squared. 3t squared becomes 6t. 36t becomes negative 36, and 50 goes to 0. We just use our calculator, use math 9, okay. Definite integral from a to b. So if we do math 9, a to b, that's from 0 to 5. And then to get to that absolute value feature, you're going to go to math number ABS. So math number ABS, and then we can just type in that velocity function, 6x squared plus 6x minus 36. Close that off with dx. Hit enter. It may take a second, but that result will give us that total distance traveled by this particle in those two time intervals, counting all the places where it goes back forwards and backwards. So 232.9 rounds to 233.